Hello, my name is Carlos Cardoso and I'm here to present the chapter 10, Bet Sizing of the book Advances in Financial Machine Learning as an assignment, individual assignment for the computational finance science at Nova EMS. So let's start. Uh, the motivation of this chapter is to bring some light about the bad side of our machine learning algorithm or bets in the market. In the beginning, we try to illustrate this with some examples, like a machine learning algorithm can achieve a high accuracy, but if you do not size your bets properly, your investment strategy will inevitably lose some money. How we can see this? We have one supposed here that one strategy produce a sequence of bet sizes like M11 and M12 and M13, like 0.5, 1, and 0. And the market price followed a sequence of price like 1, 0.5, and 1.25. These are the prices at time t. So, and we have another bet size different that the one that we started like that produce the sequence like 1, 0.5, and 0. So here we can see the difference of each other. The first bet size algorithm brings us these two here, and the second brings us these two here. So what you can see that both strategies produce the same forecast. I mean, we do not change the forecast of the prices. So we use this forecast of the prices here, and we have 25% of upside. However, the first algorithm made money, 0.5, and the second lost money. The loss is minus 0.125, 12 and 5. So that's how it is. That's show us how important it is to have an algorithm that make our bets properly and more with more accuracy in your time. Okay, so for this, the chapter 10 brings us three approaches for strategy bet sizes. So we have the first approach is the mixtures of two Gaussians. The second is budget approach, and the third one is meta labeling approach that we can need a little bit more examples. So the first of all is the two of Gaussians. So here, in general, we should prefer to size a position in such a way that we reserve some cash to possibility that the trading signal strengthens before it weakens. So what's the rationale here? What we can think here? It's before we have a large position that makes us in some time take a position that is much bigger that position should be. To make this properly, we should compute the series of the concurrent long bets and the concurrent short bets at the time t. So we make the series and bring this this function here. So if you have this factor, that will give us the number of concurrent long beds and the concurrent short beds. We divide and make this factor. So after have this work here, if we could fit the mixture of two Gaussian values. So for example, we could size the bed as 0.9 when the probability of observed signal is greater value, it's only 0.1. The stronger the signal, as the stronger are the signal, the smaller is the probability that the signal becomes even stronger. Hence, the greater the size bed. So that's the rationale behind this. It's, if I have this signal that is strong enough in my concurrent sequence, like observing my concurrent sequence of long beds, we should have a size that fitted this model. Because if this signal is strong, the probability of this signal become more strong, it's small, and we should have a higher position for this. So that is what brings these mixtures of two Gaussians approach. The second one is the budget approach. Okay, the budgeting approach compute the maximum number or some other quantity of concurrent long beds. You can see here it's similar to the other one. And the maximum number of concurrent short beds. Then we derive the bed size as this function here. So the goal is that the maximum position is not reached before the last concurrent signal is triggered. So we have this function here. We should have we should have this design and follow this model here to make our bets. So also have bets we can be greater till the last concurrent long position reached. So that's the budget approach. For the third one, it's meta-labeling approach. So it's fitted a classifier to determine the probability of misclassification and use the probability to derive the bed size. So this approach has a couple of advantages. Like the first one, it's the machine learning algorithm that will decide the bed independent of the primary model, which just allow the incorporation of features predictive or false positives. And the second advantage of this model is the predicted probability can be directly translated into bed size. So how can we do this? Here we have like the bed size from predictable probabilities. Okay, for two possible outcomes like x -1 and -n1. To test, we should test the new hypothesis, like hypothesis 0, it's p x equal 1 and equal f. We should compute this function here, okay, where z represents the standard normal distribution, and we derive the bed size as this sequence here. So once you have this, we should have a graph like this, where we have the bed size predictable from our probabilities, right? An important question about this is to average activity beds. So the question here is all bets are associated with holding periods. So override old bet as a new bet arrive. That could lead an excessive turnover, right? And then we should have sensible approach to average all sizes across all bets. And these bets that are activated. What's the mind behind here? It's also have some bets, and our model bring us new bets. We should not override all the time these bets because we're gonna trade it a lot. So we should average these activity bets for a model. So this strategy could reduce our turnover, but bring small trades will be triggered with every position. So it's a good model, but it still have a lot of traders in this kind of average bet size. So here we have a model that become more like this. If you compare to this other graph here, it's a little bit different because the suggestion here is to discretize the bet as this formula here, and then determine the degree of the discretization. So the goal here is make average of all bets and reduce the turnover in the override traders. So in the chapter bring us another example of how we could solve this kind of override trades and etc. The point here is we should recall a triple barrier labeling method presented in chapter 3. In certain periods, until the outcomes takes place, the price have some fluctuations. So, and once you have some positions, another forecast may be formed. So we should adjust our bet sizes as the market price fluctuates. So imagine if you have some forecast at time t0, right? And at time t0, I have one bet, one signal. And at time t1 and at time t2, we have another forecast for the same position that we had already. So the idea here is to bring of our machine learning algorithm a method that can make some adjustments in your initial position, right? So that will derive other limit price. So to implement algorithmic compute dynamic position, the limit price is a function of the price in the time pt in the forecast fi, as I said. So first we calibrate the sigmoid function so that it will return a bet size, in this example, like 0. No bigger than 0.95 for a price divergence of x equal 10. Second, we should compute a target position of a maximum position equal to 100 here. So after that, if you try like the forecast 110, we'll get only 9.5. This is a consistent calibration of the model, right? After make some some calculus because we have to use this method. Uh, we have to make some calculus and bring us this function here, right? Uh, After that, we have this function sigmoid and concave and to convex, and fx are equal this function here, and we should have a graph like this about our bed positions and our bed size, right? So this is the chapter 10. We have here some exercise and some examples more detailed. This is just a little bit review of this chapter that brings us those three methods to calibrate our bed size. We have, of course, more simple and more complicated. The more efficient should be meta labeling that bring us not reduce the bed sizes, the traders, but make some adjustments as a new forecast outcomes. We should incorporate this on our machine learning algorithm. So this is my review. Thank you so much. And this is it.